Right, first of all, thank you very much to Region 9. And this is a joint webinar with AACI and ourselves at HKA. The starting point, obviously, for this is the linear scheduling methodology for delay analysis, which my colleague Dimitris is going to give you an insightful talk about that. So we're going to look at what we're going to talk about in the first instance, a little agenda, and in the first instance, maybe just give you an overview of HKA. For those that don't know us, we're over 1,000 people. We've got 500 plus consultants and advisors, 500 plus experts, quantum, forensic accountancy, technical, and we've also got access to a further 200 to 300 specific technical experts as well, which is quite a feat. Our reach is over 7 continents, 40 odd offices, and in 18 different countries. So 100% of the top law firms we work for. And the kind of interesting stat there is over 100,000 project disputes, 100,000 project disputes resolved, and really sizable projects at that. We are in the who's legal with ranked number 1 with our construction expert witnesses for the past 7 years, and that gives you a quick overview of the HK business. So the agenda, what we're going to talk about, I want to give you a bit of a scene setting in the first instance. This is a bit of an insight to what we've got as a business, which is our Crux analysis. This will set the scene for the discussion that's taking place. Quick overview of the global issues, specific insight within linear projects, and then to the main event that we're all looking to listen to. So what is Crux? Well, Crux is our own internal research program that we do. It looks at the primary and secondary causes of disputes on major capital projects around the world. This year's report is called Forearmed, Forewarned, and it looks about 1,800 projects worldwide. We look at the next slide. That gives us, the Crux report gives us that insight, and it examines those causes of claims and disruption and disputes on the major projects. It gives us the ability to actually better serve our clients because we can
Michael, you're muted again.
Apologies, I don't know how that happened. I'm going to move on to the next slide because I don't want to repeat that. Wasn't quite sure where we were because the headline figures of what our Crux report is all about is quite significant. We've got over 1,800 projects that we've looked at as part of this study. It goes over 106 different countries. It encompasses 2.2 trillion worth of capex costs, and remarkably, we have totals of plus 875 years of extensions of time being claimed and 91 billion in costs being claimed. So quite a significant realm of dispute there. These are the top five causes of disputes that have arisen within this year's report. No experience that changes in scope is obviously sitting at the top. But interestingly, you'll see here the design elements, design incorrect, design information late, and design incomplete. They stand within those top 5, with contract interpretation issues sitting there at number 5. We'll look at the next slide. We've highlighted there, really, scope change at the top. But as I mentioned, the incorrect, late, or incomplete design information, when combined together, that triple whammy shows that design-related delays and claims are in excess of what we're seeing in scope changes alone. Okay. Top regional causes of claim. I'm not going to go through this. This is for you to consume later. Similar heads of causation, but spread differently in different regions and different sectors. Now we're going to come on to linear projects, and looking at linear projects, what do we mean by linear projects? Well, the characteristics of those linear projects, it's longitudinal, spatial, and repetitive construction activities. For example, tunnels, pipelines, bridges, rail and transport, and roads and highways. That's what, under our Crux data, that's how we classify it. It's the repetition of those activities, and it's highly dependent upon efficient production rates and optimum resource utilization for those repetitive activities. So that's the key. That's the key to consider there. The next slide, what we've looked at here is we've looked at linear versus non-linear projects. The number of projects was examined at the top there, 306 relative to 1,537. The interesting fact for me is the spend profile, that despite the linear projects only equating to 20% of the non-linear projects, the spend is slightly higher at 1.44 billion. The average EOT claimed, again, relatively similar, 4-5%, a difference between the two, where EOT being claimed 62.4 and non-linear projects 66.9%. Average cost is pretty much the same there as well. Now, when we look at the actual top clauses, we have change in scope being relative to both cases, but that's where it starts to diverge slightly, because obviously in linear projects, there's more restriction with access, maybe in terms of physical conditions where they were unforeseen, and design being incomplete, or indeed the design information being late. Now, is that because there is a less series of activities there in comparison to the non-linear projects? We'll leave that one out there for you to have a think about, and maybe when Dimitris explains his content, that will become even more apparent. The next slide. The next slide is, again, it's just to give this gives you the top 10 global causes between linear and non-linear projects. The one that jumps out to me that is not in the top 5, but is contract management and administration, or poor management of subcontractors. So whilst we have got activities there with scope change and design issues quite heavily biased in the top 5, there's still remains that that human-based element of administration of the contracts that cause or a dispute level of situation. Okay, so if we move to the next one, you can click on this to your heart's content and look at some of the Crux dashboard that we have. The report is on the click at the below, and it'd be interesting when you go through the dashboard yourselves in your own spare time. How does that reflect with the projects you're actually on? How does the data that we see in our sectors, in our geographical locations, how does that compare to your own? Be interesting for anybody to give their feedback on that, on what they see and if it's comparable on their own project. Okay, now we'll move on to Dimitris, and I'll shut it up.
Michael, thank you very much for introduction, and the data extracted from Crux and the comparison between linear and non-linear projects, and especially the element about the restricted areas and the site access and the soil and the unexpected soil conditions as causes of delay or causes of dispute in the linear projects in comparison to the non-linear is a point that I will be talking later on. Anyway, as an introduction, my name is Dimitris Tousiakis. I'm a partner of HKA based in the Dubai office, and I am a delay expert, having a long-term experience in analyzing delays in various types of projects, including linear projects like roads, railways, bridges, etc. So in this presentation, I will try to explain the difference between the common and most used method called the critical path method that most people are familiar with, and the linear scheduling method, both in terms of planning and project, but also in terms of forensic delay analysis, which is what we are dealing with, and how we can use the linear scheduling method in analyzing the delays forensically in a linear project. At the end, I will present a case study of linear scheduling method application on a bridge construction project in order for you to understand a bit better and see the graphs and graphically understand how LSM can be used. But first of all, let's start from the basics. What is delay analysis used for? In general, delay analysis is used for examining the time loss of a project or an activity. In order to assess the impact of the changes and delays on a project, someone needs to carry out a delay analysis. This involves a critical path analysis, where we identify the critical path activities, which then enable us to, and the legal teams, to focus on the critical delay events and save time rather than investigating all the delays of the project. You know, as you probably know, there are a lot of delays in various areas of the project and require factual investigation, which are time and money consuming. So finally, delay analysis is also used by the parties in a dispute to support or defend an extension of time claim, and by the delay expert to support their expert witness evidence given in court, arbitration, or other proceedings. So this is what delay analysis is used for, but I'm pretty sure many of you have heard the term, oh, delay analysis is a dark art. Is it really? Or should it be really? Delay analysis methodologies with different names. For example, the AACE International recognizes 9 different delay analysis methods, while the Society of Construction Law Protocol recognizes 6 analysis methods. And in many cases, there are just different names for the same thing, or different things with similar names, and this creates some confusion. But why should we complicate things? Tribunals and courts and arbitrators prefer non-complicated and easily understood delay analysis. These typically rely on factual evidence, some basic engineering principle, and most of all, common sense. People need to understand what went wrong practically and what delayed the completion of a job. So the key takeaway is delay analysis is not and shouldn't be a dark art. It should be easily understood by a layman and someone who has not been involved in the project. But how do we do that? So that's the million-dollar question. Typically, the method that is mostly used and people are more familiar with is the one that is used by planning software like Primavera, Pre6, or other similar software, planning software, is the most known and used scheduling method in construction management, and you come across it in most cases where people use this software. So with this method, schedules are prepared by inputting data for individual activities. For example, the duration of an activity, the dates, the logical relationship and dependencies between the activities, etc. You put that into the program, and the software then automatically applies algorithms to calculate the free float, the total float, the critical or near critical paths, and the projected completion date, essentially. So the critical path method is a valuable tool that can display graphical visualizations, normally in a form of a Gantt chart, like the one you see on the right-hand side of the screen. These Gantt charts, you can see, is like one dimension overview. Basically, you have the time on top. If I point, here are the dates and here are the activities. Now, the SEL protocol determines the critical path method as the methodology or management technique that, through the use of calculation rules, usually automatically carried out by programming software, determines the critical path and calculates float. The typical graphs we come across are these ones, which is an extract of Primavera P6. And basically, for a very simple pipeline project, which comprises of excavation in 3 areas, then pipe laying works in the same areas, backfilling, then we have the construction of a culvert, and basically there is a site restriction for a period of time in a specific area. So when we put in the program the data for each one activity, the program automatically creates the activity bars, the arrows between the activities, which is the logical relationships, and identifies the critical activities, which are shown in red, and the non-critical activities, which are identified in green. This is useful. Most of us are familiar with that, and we use it in most of the projects we come across, both for planning and forensic delay analysis. Now, what is the linear scheduling method and how it compares with that? So the linear scheduling method graph display 2 axes, one for time and one for location, which is the chain nuts, basically. This is a less known method and used for scheduling linear projects or where repetitive activities occur, and optimal productivity rates are essential to achieve timely completion. As you can see, the graphs are 2-dimension graphs. We have time on the y-axis and location on the x-axis. And using exactly the same example we used in the previous slide, the same pipeline project, divided in the 3 areas here in the bottom, you can see that how things were planned to happen. So here's day 1, 2, 3, etc., etc. And you can see in brown is the excavation. So excavation in area 1 was planned to start at the beginning and finish in day 5. At the same time, the excavation in area B would start and finish at the same time. However, excavation in area C would start on day 7 and finish on day 11. And then after doing the excavation, we can see the pipe laying activities, the backfilling. So these gradual lines are the activity lines. Here, we can see activities that happen in a specific area. So at the chain nuts 1600, we can see a bar, which is the construction of the culvert, as you can see here. And also, we have the restricted access, which is the block at area C. So basically, by inputting all this information in a graph, we can see how we can avoid lines crossing the culvert, because we cannot do any other construction when constructing a culvert, and also we can avoid construction activities when the areas are inaccessible. And how steep are the activity lines depicts how quick or the rate of progress. So basically, to summarize, the difference between critical path method and the linear scheduling method. So critical path creates 1-dimensional graphs, which does not visually provide information about the physical layout of the site or any potential constraints or other parameters, and doesn't visually and easily demonstrate the productivity rates for construction activities. On the other hand, the linear scheduling method is a 2-dimensional diagram that enables the avoidance of impact from space restrictions, as we discussed, like the construction of a culvert or site access. It demonstrates optimum productivity for all activities. It helps achieving optimum productivity for all activities. and ensuring that one activity doesn't adversely impact on the production rates of the others. And with this method, we can ensure continuity and uninterrupted working of resources by moving the resources from one location to the other. And it's easier to understand from the linear scheduling graph compared to the critical path method. So this was for planning of a project, but how linear scheduling method is used for forensic delay analysis. As you know, construction dispute resolution processes often require a retrospective delay analysis to demonstrate the effect of the delay events. So basically, the analyst or the expert needs to look backwards to understand what happened. So linear scheduling method used for forensic delay analysis of linear projects can display valuable insight of the actual progress of the works in relation to location. And this is the big benefit here. The LSM can graphically depict the changes in the production rates by seeing the change in the graduity of the lines and the interrelationship between the resources, locations, and duration. LSM visual representation are easily understood and read, even by those with little or no experience in the construction program management or project-specific details. So let me, I hope you understood what LSM is in general, in principle. So I will try to explain this even better through a case study where we applied during a forensic delay analysis of a bridge construction project. So the bridge was constructed by application of the span by span bridge construction method. As you can see in the photo to the left, we have the piers constructed, and then we have the launching girder on top, which basically erects the platform segments and creates the platform segments. And as it creates the bridge, the launching girder is moving forward till the end and continues. On the right-hand side is a graphical representation of this. So basically, the construction sequence starts with the underground piling foundation. Then we have the construction of the piers. And on top, we have the launching girder, which erects the platform segments and creates the platform. So you understand that in order for the bridge to be completed, the main activity and the main activity we should track in order to see how things were progressing is the erection of the platform segments by the launching girder, because this is how the bridge is constructed. So what we did for this analysis, we created the two-dimension time chainage graph using the linear scheduling method. You can see on the left, as we discussed, the time, the months of the year, and on the at the bottom you can see the location, the chainage. So we will make, and this is only the planned and actual bridge platform lifting by the launching gear. So observations. Just by looking at this simple graph, with the dotted line, you can see that the plan was to start in July 13 and having this production rate finish in October 14. So there was a planned duration of 50 months starting from location A to location G. Now, this is what actually happened, which is the continuous line. The red arrows highlight the periods of low productivity. In other words, the steeper the steeper gradient then shows that things were delayed. So whatever is vertical, whatever goes up is a delay. Whatever goes flat means that it was completed more quickly or according to the planned rate. So here you can see this took longer to be constructed. This was according to the plan. this period here, for some reason, it was lower productivity, lower rate of progress, and then this was as planned, etc., etc. Observation number 3. At the beginning of the project, there was 1 month of delay. So instead of starting in July, it started in August. Then we can see here that the launching girder reached at location C, where basically there was around 3 months of stoppage. This is another observation. Then the launching girder proceeded to location D, where basically there was a stop. Then we can see that the launching girder, after 2 months, instead of continuing from location D onwards, it moved to location E. So basically, the contractor either decided or was instructed to divert from the planned sequence and relocate the launching girder to location E, which all this situation created a 2 months delay. Then the launching girder proceeded to location G, and then it moved back to location E and proceeded all the way until here. And we can see that from G going back to location E, it was delay 4, which was approximately 1 month. And then eventually the bridge platform construction completed at location D in May 2016. This is 19 months later than the planned completion of October 14. So just by creating this very simple graph, we have an overview of the delays of the most important activity, which is the construction of the bridge platform. And we can then focus on the periods, the red periods here, where the big delays were, or in the periods where, we have the red arrows, where basically the rate of progress was slower than planned. Now, okay, we have this, but then what else can we do with this linear scheduling method to investigate even further? What were the causes of these delays? So we can enrich this graph by adding much more information. And this is the next slide. I know it looks like a mess, but don't be scared. And basically, this gives the information of what happened. Because what we have here is the same graph. The dotted black line is the planned launching girder. The continuous black line is the same as the previous graph. But now we have enriched the graph with areas and periods of lack of access, here and here, the gray ones. We have enriched the graph with the actual piling design. So basically, we can see that the piling design was typically taking like 3-4 months. But in this location here, for some reason, between 1,250 and 1,500 meters, it took much, much longer. And also, we can see in green is the actual pile construction. So when the piles were constructed, and in blue is the construction of the piers. So now we have taken all the information, we have put it in the graph, and we can draw even more conclusions from this. Basically, you can see here, we said that there was a delay at the start. So could it be because of the lack of access? Possibly, because then after having access, you could only start building your piles and your piers, and then you could start your launching girder, considering that there is some time to install. And you can see that while there was no access here, even though the contractor planned to start here, they started constructing the piles in the locations after. So the contractor was progressing with other piling work, but they couldn't really start the bridge construction until the access issue was resolved here. So this could be the potential reason for delay number 1. Then, for the delay number 2, we can see here that the piling design took so long and was only resolved here in January 14, and then the contractor constructed the piles and the piers, and this could be the reason why the girder stopped at location C and waited for 2 months for the piers to be constructed and then continue. And obviously here in location D, where there was the big stoppage and the contractor was instructed to relocate. So we can see here that there was lack of access for so long that when the girder reached at location D, the piles weren't even constructed pretty much. And then we had to construct the pier. So the contractor or the engineer or the employer instructed the contractor to relocate in location E until all this is completed. And we can see here that the launch girder continued, and then when all these were completed, it finished the project at the same location. So you can see here that by inserting all this information, you get an even better understanding of what were the potential causes of the delay and where. So there is the correlation between areas, lack of progress, and big delays. Of course, you can enrich this graph even more by inserting information like the soil conditions. So for example, if this was, the progress was slower than planned, maybe it was because there were the underground conditions were rocky, while the rest of the project, the soil was soft. So maybe the contractor didn't expect to find hard soil conditions. So this could explain the delay for the slow progress from A to B. And also, a long time, we can plot the number of available resources, or maybe the production of concrete segments from the factory, and then we can correlate this with the actual progress and draw more conclusions out of it. So you can see how this little graph captures so much information, and you can draw so many conclusions which can easily be presented and understood. So imagine going to the arbitration or to the court, presenting this graph, or going to your client and employer, or you want to present a claim, explaining the story. This graph tells the story so clearly, much more clearly than the bar charts. However, it's not the answer. It's not always the answer. LSM has its limitations, especially for forensic delay analysis. First of all, it requires available and detailed and accurate records, and actually in the correct format. So to create these graphs, you need to have information about when the launch girder progressed and where it stopped. You need to have information about the design, the restrictions area, the construction of the piers, and all this ideally should be in the correct format, so someone can insert all this information into this time chain as graphs. If not, it will be hypothetical, and if it's not in the right format, it will be very, very time consuming to create these graphs. There are some software tools available that use time chain as graphs, but you can even do it in Excel. For example, this analysis was done in Excel. Now, the other thing is that in contrast to the critical path method, the LSM is a graphical method that does not rely upon an underlying mathematical model. Consequently, the conclusions coming out of these graphs, especially regarding the critical and driving activities, are based on the delay analyst's observation, construction knowledge, experience, and common sense and understanding of the graph, rather than automated software calculations, where, for example, when you have a bar chart and you're using Primavera P6, literally by the click of a button, you get your answer about the critical activities and the forecast completion, etc., etc. However, from our experience, it's very rarely that these are accurate, because projects become so complex, and the critical path method programs and softwares are getting so heavy and so complicated that 9 out of 10 times there is an error there, and it doesn't calculate, or it doesn't take into account the number of gangs working in parallel, etc., etc. So LSM is useful, but it doesn't give you the answer automatically, but it can enrich a position, and it can also help you identify what really delayed the job. This is the end of my presentation. I hope I helped in understanding the difference between the critical path method and the linear scheduling method in the use of forensic analysis of linear projects. As a final point and a personal point, I would like to dedicate this presentation in memory of Apostolos Stigas, who was a pioneer of human resources, a mentor to me, and a great man who was my father-in-law and passed away 3 days ago. Sorry for that, and thank you for attending the presentation. I hope you found it useful, and please feel free to ask any questions you have to Michael or me. Thank you very much.
Thank you, Dimitris. That was excellent.
Thank you both. There was a question on the Q&A tab. A question or a comment from Hamed, just stating that LSM chart, however, it is more clear in terms of time and location sequence. The critical path is still not identified.
Yes, that's true, and that's probably that was a comment before my final slide about the limitations, and that's true. It is more clear in terms of time and location, but it doesn't provide the critical path. However, by looking at it and by reading the contemporaneous documents and the correspondences, etc., someone can draw conclusions, and maybe with the use of a critical path or method and Primavera P6 can also support a position. For example, in the case study we demonstrated, it was obviously that, when the launch gear stopped and had to relocate and then travel to the other direction, obviously that was the critical delay at this time. So I agree. It's not automated calculations that gives you the critical path, but then again, even Primavera P6 schedules, they might give you an automated answer, but is this always right? I highly doubt it.
It adds value as well to disruption elements of claims as well, which is it provides a real good graphical representation of some of the issues that transpire.
That's true, and with the how steep these lines are and the rate of progress is an indication of the progress. However, when you overlay this with information like the resources or the production of a concrete segment from the factory, then you can assess the productivity. Other than so then when you go into the productivity analysis, it is a disruption analysis and can demonstrate where disruption happened.
So we have a couple more here on the Q&A tab. Let me just see. One from Saifin asking if LSM can be used for non-linear projects.
Well, it depends. I mean, it depends on the definition, but we have used similar to LSM for high-rise buildings, which could be also considered linear project because the trades might start from lower ground going up. But with high-rise buildings, for example, it could be applicable at the beginning, but then when the concrete is complete, then the MEP gangs and the other disciplines work all over the place. So it's not really helpful. It gets very messy. So it's very much suitable for projects like bridges and roads and railways, but for buildings, could be used for the concrete construction, for example. Yes, or until the MEP starts. Yes, it gives you some information there.
Yeah, if you don't mind my comment as a planning and scheduling professional, anything that is repetitive, pretty much can be represented on a linear schedule. For example, if you are talking about a wind farm, which just by the name and imagining the wind farm and being constructed perhaps does not sound and does not seem linear, but in the end of the day, it's about site access roads, concrete foundations, installing the turbines and the towers and turbines so it's a repetition, the same as you mentioned, high-rise building, same approach. Just taking this note to mention that there are a couple of articles published on AACE library that touch that linear and repetitive topics. So for any further clarification, I think it's important to highlight that. And then there are a couple more questions. I will try to group them. There is one from Zaka and another one from Emad, but I believe it's touching the same thing, which is what is the recommended tool for developing the delay charts and what software you use or advise to produce such LSM charts?
Yeah, as I said, depends on how complicated you want to make things. I would recommend keep it simple. So don't include too much information, because then it will not be easily readable. So, and for the creation of this case study, it was all done in Excel. However, there are software like Tylos, which is actually a planning software as well, using linear method. To be perfectly open, I'm not too much familiar with Tylos, but I've been using another software called TurboChart, which is not a planning software per se, but it creates the graphs, the linear the time chainage graphs, and actually can export information from P6 directly to TurboChart. But as I said, I would recommend keeping it simple and not include too much information.
Good one. Then we have Stephen asking regarding formal disputes, is the LSM generally accepted or is the CPM still preferred?
I think a combination is always useful. With the LSM, you can demonstrate to a tribunal or an arbitrator very easily what happened. When you see, for example, this big lack of access period, it's much easier to demonstrate that to the arbitrator. And basically, if then the project was stopped at this point in time, then it's pretty obvious that what was causing this lack of access, I don't know, maybe the design or something, this was the critical path and the critical delay for a long period of time, if not for the whole project. So from my experience and from a rail project I have been involved in the UK, it was the construction of a specific bridge. Even though the railway was so big, you could see on the graph everything was going fine, and then suddenly there was a big line there and everything stopped. It's pretty clear that the whole delay of the project, or most of the delay of the project, was caused by this bridge and the construction of this bridge. So a combination of both is typically the best way forward, I think.
Good. We have 3 more questions. One from Maris. What is better sequence to create the schedule in P6 and then import it to the LSM, in this case Tylos, or vice versa?
Usually, I mean, if you are doing your planning and it's the beginning of the project or the or you are progressing with your construction. I think P6 and Tylos at the same time would work. However, for retrospective analysis, in many cases, we don't have linear scheduling graphs, so we have to use P6 and export it into a linear scheduling method. So I'm not sure if there is a clear answer to that. I think it depends on the situation, really.
Then Martin, how do you treat areas of concentrated activity such as junctions, roundabouts, etc.?
Yeah, that's a good question. So similar to the first pipeline graph, when there was a culvert, for example, over there we can overlay some vertical activities for the construction of, secondary roads or diversions or roundabouts as bars rather than activity lines. So it is getting a little bit messy, but this is how it's done. And also, in the case of the bridge, it was easy because it was one main activity, the launching girder, and you trace this direction of the bridge segments, and you could see what was happening. But in a big highway where we have junctions and roundabouts, then we need to think of how we will demonstrate all this in the same location. Typically, we manually offset a little bit just to show the lines close to each other, if that helps.
Yep, I think some of the tools also allow you to obviously to plot just that roundabout and highlight the roundabout specifically if needed. And then I think the last question, as we are also heading towards the end, it's from Angelos. Let me try to. So critical path after studied and being logic in planning software, like P6, can be illustrated in Tylos.
That's true.
How evolved and changed. Yep.
Yeah, that's true. I mean, if you think that planning software and the critical path and the forecast, you have program updates, all these can be traced in time chainage graphs, like by use of Tylos or any other software, really. And yes, it's great for demonstrating the future activities or the remaining activities as well towards the completion of the project, and can be illustrated in Tylos what is critical or not. But I'm not sure if Tylos or other linear scheduling tools really calculate the critical path. It is the P6 that calculates the critical path. Of course, can be demonstrated in a time chainage graph, but it's not calculated by it.
And I think that's it in terms of questions.
Okay. Thank you very much for all those that listened in. And I think we can make the slides available, Yoe, and if anybody wants to reach out, please do so.
No, absolutely. I mean, any questions afterwards as well? I will share my direct email for AACE International, but also as Dimitris and Michael are sharing their own emails, feel free to reach out. Great session, guys. Thanks a lot once again, Mike and Dimitris. It has been a pleasure. I think a very useful, definitely session, and thank you to all the attendees for taking the time and being here. It was
Thank you very
great.
much.
Thank you.
Thank you very much for having us.
Thank you, Nate. Thanks.